Let's start with page 3. This is page 3, yes. And number 7. So in page 3, number 7, oxalic acid is a diprotic acid with a chemical formula H2C2O4. Now, it doesn't matter whether you know it does matter if you do know the chemical formula, but you don't actually need it in chemistry of solutions that much because you will have all your data given, but it's important to understand this, okay? So as soon as they tell me that it's a diprotic acid, all I have to do is H2A because this will apply to all diprotic acids. And it has a molar mass or molecular weight of 90 grams per mole. So you need 50 ml of 0.1 molar NaOH to totally neutralize the acid. This is the most important word in this question. Why is it the most important word? Because you have to understand that you have a diprotic acid. It means you need H2A to be neutralized and then HA minus to be neutralized. Write the equations if you need it. But it basically means that the number of mole of HO minus needed to neutralize, completely neutralize the diprotic acid is the number of mole needed to neutralize H2A and to neutralize HA minus. So it will be double the number of mole to neutralize H2A. This is how you understand it. If you don't, go back to the rules that you learned before. Write down the complete equation, which basically says that H2A, if you need verification, like to completely neutralize it, you have to react it with 2HO minus to give you A2 minus plus H2O akid. And then do that stoichiometry thing, number of mole of HA equals number of mole of HO minus divided by 2. But the logical thing to do is to recognize that the amount of HO minus you need has to neutralize H2A and it has to neutralize HA minus. So basically, you will need double the amount in order to neutralize, which is what we wrote here. So what is the moles of HO minus? It's basically, it's the mole per liter. I'm not gonna switch out the units now. You already know you cannot cancel units unless you change them. So let's change the milliliters so that no one makes any mistake. And that's equal to 2 times what is basically the moles of HA. Remember that they want the moles or they want the mass, the grams. What is the grams? What is the mass? You already know that the moles is basically equals to the grams per gram per mole. Okay, so that is the number of mole. Do I have it? It's right there. So it's the mass by the molar mass. Simply solve the equation because you have only one unknown and you should be able to get the mass. I think it's around 0.22 to something grams. Again, I'm not doing the calculations, you do the calculations, okay? So it should be around 0.225 grams. Which one is that? It's C. Number 8. Oh, you have a lot of space for number 8, so number 8 probably needs a lot of space. Calculate the pH of the following solution obtained by mixing. Okay, obtained by mixing. You have a strong acid or is a weak? It's a weak acid. You have a weak acid, PO4 3 minus, it's a base. You have a weak base, H2PO4 minus, it has both acid and base properties. Whenever you have something like this, the first thing that you do is just put the pKa scale in front of you because you have to determine which species will react first. In reality, HA is an acid. It can react with the base, which is PO4 3-. H2PO4- has acid properties. It can react with PO4 3-, and H2PO4- is actually also a base, so it can react with HA. What determines which reaction will predominate the system is the Kr, which is the equilibrium constant of the reaction. The higher the equilibrium constant, the more predominant a reaction is. First thing that you do is to put on the pKa scale. That's the first step, pKa scale. And you start by putting all of them in. In the pKa scale, I have 2.2. I have 2.8. Like you don't have to stick true to the scale, okay? I have the 7.2, and I have the 12.4. Very good. So the 2.2 is basically phosphoric. Remember, right hand, it's the acid, H3PO4, H2PO4- the base. 2.8 is HA, so it's basically HA, A-. 7.2, who is second couple, which is basically the acid of the second couple, is H2PO4-, base is HPO4 2-, third HPO4 2-, PO4 3-. These are all the couples that you have in your system. Now what you do is you highlight the couples or highlight the species that you have an actual concentration of. Killing, they exist. However, some of them exist in neglected values, others exist in substantial values. Highlight whatever exists in substantial values. So I'm going to basically highlight in a single color, أول شيء HA. هيدي step 1. I'm going to highlight HA because this exists. I'm going to highlight PO4 3- because this exists. And I'm going to highlight H2PO4. H2PO4 has 2 positions, one where it acts as an acid, one where it acts as a base. Remember, bases do not react with bases. Acids do not react with acids. Okay, what do I mean by that? HA will never react with H2PO4- in its acidic form. It can react with it in its basic. So, first rule, acids and bases, acids and acids, bases and bases, they don't react. Second rule, when you want to go for the reaction that actually happens, choose the reaction that happens along the gamma direction. Remember how you draw the gamma? Gamma is drawn like this. Anything that happens in an anti-gamma direction will be very limited. So the second rule is the gamma direction. The third rule is the biggest distance between KAs, because this will give you a bigger KR. What do I mean? According to the gamma rule, I have 2 options. My first option is PO4 3- will react with H2PO4- to give me HPO4 2- and HPO4 2-. That is the first one. The second one will be PO4 3- with HA to give me A- and HPO4 2-. And look, I said the first one and I said the second one, but I did not mean that the first one will happen first. So I said that this is the first option, and I said that this is the second option, but I don't mean that the first option will happen first and the second option will happen second. The reaction that will predominate is the one that has the biggest distance between its pKa's. And in this case, It's this. At the distance هون, that is the distance هون. Because remember, for a reaction along the gamma direction, Kr will equal 10 to the bigger pKa minus the smaller pKa. In the first one, it's 12.4 minus 7.2. In the first option, which the first reaction that predominates the first option. Kr of the second option is 10 to the power 12.4 minus 2.8. It is very clear that this is the larger Kr. So this is the reaction that will predominate. Take this rule if you need. I prefer that you understand the derivation of it. It should be in your actual course. But take this rule. It's very easy to follow. You will never make any mistake. Remember, the condition for this Kr is that the reaction follows the gamma direction. So let's start. All of this was an explanation. The reaction that will truly happen is the one that we said it's the second option, but it is the predominant reaction. It is the predominant. This is the reaction that will happen first, which is basically PO43 minus plus HA. I'm going to leave this area void. Okay, هيدي الاريا اللي هون. I'm going to leave it void for now, and it will give me A minus and HPO4 2 minus. Are we agreed? No. Why did I leave this area void? For a very simple reason. I have to know if the reaction is complete or not. If the reaction is complete, and if it's not complete, this is what will tell me how the reaction will behave. If I have to do a minus X, if I have to do the ICE table, or if I simply just get rid of the initial values. What determines this is the Kr, which we've already said it's equal to 10 to the power 12.4 minus 2.8, which is basically 9.6. It depends on the rules that you took this year, because this is different for every curriculum. If this, I think the normal rule is that if this is equal 10 to greater than 10 to the power 4, consider the reaction complete. I remember in your system, 10 to the power 4 is quantitative, 10 to the power 6 is complete, but they do make the agreement that whatever is quantitative, let's consider it to be complete. Because this is considered to be complete, this reaction is governed by a single direction arrow and not by a reversible arrow. As long as you don't have a reversible arrow, it means that there's no minus X plus X. Simply start initially. I had 0.01 molar of this quantity, and remember, the only reason I'm using molar and not, the only reason I'm using molarity, it means concentration, and not molar, is because the volume was not changed. So I can consider molarity and mole the same thing because the volume was not changed. So initially this was 0.01, this is 0.02, nothing, and at the end it's basically, this is the limiting. This will become what I call to be approximately 0. This will be 0.01, this will be 0.01, this will be 0.01. That's the first one. Second, you don't go to the second option that we had, to the second Kr. No. Now you register what are the real values in your system. And the real values in my system now belong to, the first thing is PO4, 3 minus is now a negligible value. It doesn't exist anymore. Well, it does exist, but not considerably. Okay? So, the second thing, highlight everything that exists. I still have HA, 0.01 molar. But now I have A minus, 0.01 molar. And I have HPO4, 2 minus, again, 0.01 molar. Remember, I still have H2PO4 minus, which is 0.01 molar. Choose the reaction that will happen according to the gamma direction. And you look at all of this. When you look at all of this, you will see that there is no predominant reaction along the gamma direction, actually. Not one that was new. So what is the new one? Just a minute. Okay, sorry. Okay. So as I said, we highlight all the new species that exist, and we look at the reactions that do exist along the gamma. If there are no reactions along the gamma directions, we will go to other options. So if you look at the species, H2PO4 still exists. HA now still exists in 0.01, A minus exists in 0.01, and HPO4 minus also exists. It's a new species. Remember that the previous options, I'm not gonna erase them, no longer exist. What does exist now? Let me choose a different color. What does exist now? I'm gonna step by step say what could happen. HA could react with H2PO4 minus, but this reaction is against the gamma direction. If there is one along the gamma, I prefer to take that. It is gonna be the predominant reaction. H2PO4 minus again. HPO4 minus can react. There is a species that exists, which is HPO4 minus. It exists on the opposite side as a base, and an acid that exists. This reaction can take place along the gamma direction. Again, write it down. Second one, HPO4 minus with HA. Again, I'm gonna leave this void. A minus, the base, H2PO4 minus, the acid. Leave this until you calculate the Kr. Since it is a reaction that abides by the gamma direction, Kr here 10 to the power, the large pKa, which is basically what, 7.2, minus the smaller pKa, which is 2.8. And this is basically 10 to the power 4.4. Again, quantitative, considered to be complete, one direction. You start with initially, HPO4 minus, what was it? Where is it? It's still 0.01 from the beginning. Okay, 0.01. HA, the remaining value from the previous reaction is 0.01. A minus, pay attention, ما فيكم تحطوها 0 لأنه it exists from the previous reaction. A minus is 0.01. H2PO4 minus, it also exists, 0.01. But this is the direction that it will go to, from left to right. So the limiting value has to be consumed. The limiting is basically same thing. So you have to remove the limiting value from HPO4 minus, and this is approximately 0, or what we sometimes call as an epsilon value that needs to be determined at some point. Approximately 0, again, an epsilon value. 0.01 plus 0.01, which is 0.02, 0.02. What you have in your solution now is basically A minus and H2PO4 minus. Look at the positions. خلينا نرجع على الcolors. what I have is A minus. I'm gonna do this. And H2PO4 minus. The first position, I'm gonna change colors. The first position of H2PO4 minus is in its base. A minus is a base. A minus and H2PO4 minus as a base do not react. But there is a second position for H2PO4 minus when it behaves as an acid. However, for this particular reaction, it is against the gamma direction. It means the Kr will be very small because it's against gamma. If you have a base and an acid in the same solution with the same concentrations and with similar Ka for the acid, اللي هي 10 to the power, اللي هي I can also say pKa instead of Ka, which is 7.2 for the acid, and a similar Kb or pKb for A2 minus. We all know how to calculate the pKb of a species, which is basically 14 minus the pKa, which is 2.8. So the pKab will be around 11. If they have, and I remember that your error used to be between 100th and 1,000th, if I'm not mistaken. If they have similar pKa and pKb, and when I say similar, I mean according to the error that you have, you can simply say that the pH is half pKa of your acid, pKa of your base, which is equal to half. خلينا نبلش بالبase because it's the easiest one. pKa of the base is 2.8. pKa of the acid, go to your species, which is H2PO4 minus. It exists in both, but we already said that the reaction is happening in here. And in the first pKa, H2PO4 minus behaves as a base. One doesn't behave as an acid in the second pKa, so that's 7.2. 7.2 plus 2.8 divided by 2, which is basically 10 divided by 2, which is 5. This is the pH. If the rules for this equation is not satisfied, and you should know the rules for this equation from your course. If the rules of this equation is not satisfied, what you do is that you write the reaction, which is basically H2PO4 minus plus A minus. Again, I'm going to leave it as a void to give me HA plus HPO4 minus, PO42 minus, sorry. This will definitely be this type of error. Why? Because for a reaction with an anti-gamma, your Kr is equal 10 to the power. Flip it. Instead of doing the larger pKa minus the smaller pKa, take the smaller pKa minus the larger pKa. Why? Because it's in an anti-gamma direction. Find Kr. From Kr, you say it's equal to, what's the initial value of H2PO4 minus? Minus X, A minus minus X, HA plus X, plus X. Solve the equation, find X, find the pH. Which is why we introduced validity, because this will take longer time.